So now to example one, we are going to focus on identifying the characteristics of the cosecant as well as secant graph, and then kind of wrap up with cotangent. And we're going to identify all these characteristics of these graphs and then just kind of do a rough sketch of the graph. And if you want to go ahead and check your answer, I provided a link to Desmos where you can just kind of take a visual look into the online calculator to make sure that you got it right. So just an important thing here, we don't have an amplitude for the reciprocal trigonometric functions because they don't have a max and a min. Remember, the definition of amplitude is the half distance from the max to the min, so that is only going to apply to sine and cosine. Not all of these functions are going to have all these transformations, so if they don't have one of these transformations, I'm just going to leave it off. And then also when we're discussing the domain, we also need to discuss the asymptote, so I will kind of include that because the domain is going to be all real numbers except for where the asymptotes occur. All right, so let's go and take a look at here the cosecant graph. Just remember with all these trigonometric functions, the A, B, C, and D are always going to be in the same places. So we can say that we have a B in this case. And that's going to be helpful because when we're looking to identify the period, it's just going to be like sine and cosine. We're going to take 2 pi divided by B, which in this case, 2 pi divided by 1 is just 2 pi. Then there is no phase shift, so remember phase shift is adding and subtracting inside the function, but we do have a vertical shift because we're adding a 1 outside, so I'll just abbreviate that with a vertical transformation, and that's going to be up 1. Okay, so again, remember this 2 is very important, even though it's not an amplitude, like it's not telling us the amplitude, but what it is telling us is that the graph is being vertically stretched by a factor of 2. And that is easiest to understand by looking at the reciprocal function, because remember that cosecant and sine are related to each other, right? Especially the graphs. So if I looked at what would the graph 2 sine of x look like, 2 sine of x, plus 1, I can see that if I was to graph that, and when I'm sketching the graph, I like to kind of provide the, what am I talking about? I like to provide the reciprocal function. So anyways, we'd have 2 pi. Now, typically, the graph goes up to 1, down to -1. But if I'm stretching it with a factor of 2, now the graph is going to go up to 2, down to -2. And then if I take that graph and I shift it up 1, now it's going to go all the way up to 3. So a rough sketch of that graph would be looking something, let's just say, here's pi. So I'd probably go somewhere down here. Okay. Now, the important thing is, remember that the cosecant graph is going to be undefined where sine is going to be 0. And that's still going to occur at the pi. Just because we're moving it up, it's changing the x-intercept. But if you were to shift that down, you'd still see that has an x-intercept at pi. So that is still going to be the case in this regard as far as identifying where the asymptote would occur. So now looking into giving a shape of our graph, and I think the shape of our graph is helpful, especially when we're understanding the domain and the range. So obviously we're going to have a asymptote at 0, have an asymptote at 2 pi, and we have an asymptote at pi. Okay, so that is going to be the shape of our graph in this case. And now from here, we can kind of have a better idea of as far as what our domain and range is. So let's look at the range. So remember, the range of the sine graph is going to be from -1 to +3. So therefore, the range of my cosecant graph is going to be from, let's actually write in range. The range here is going to be from -infinity all the way up to -1. That is included, union 3 to infinity. Now, when looking at the domain, what we're going to want to do is identify the vertical asymptotes. So we can see that, if this graph was kind of shifted back down, we can see that the general asymptote for the cosecant function, this is just, for a general cosecant function, is pi n. And since the graph hasn't been changed left or right or stretched left or right, the asymptotes are going to remain the same. Like, think about it. So you have your graph, right? And if we have asymptotes at pi n, if I'm stretching the graph or shifting it up or down, those asymptotes are still going to occur at the same value because the asymptotes are going left and right. So if there's no transformation left or right, it's going to be unchanged. So the asymptotes are going to occur at x equals pi n, just like the parent graph. So therefore, my domain is going to be all real numbers such that x cannot equal pi n. And again, we include that n to represent every single asymptote occurring pi distance away from each other. All right, so now let's go and take a look at this cosecant graph here. And you can see here we have a negative on the outside, so that is going to be a reflection about the x-axis. And then I have my b is 4, so that's going to be a change in the period. So when I go ahead and do my period, I'm going to take 2 pi divided by 4 in this case, and that's going to be pi halves. So this is important because if you think about the graph, instead of it completing a period in 2 pi, it's now completing a period in pi halves. So it's going to be really scrunched in there together. And again, we're going to want to look at the sine graph here to better understand this. Besides that, I have no other transformation that's going on. Now, to kind of make my graph, to kind of make this easy to graph, I'm not going to change the scale and like try to make the graph fit, between like pi halves over here. Like that would just be not very easy to look at. So I'm just gonna expand out my scale and say, well, here's pi halves, and half of that then would be pi over 4. Now, rather than going up to 1 and down to -1 and kind of following the same pattern that we would for the sine graph, I need to now reflect that. So it's going to go down here, up, and right. So that is my representation of my reflection. So I'll just go ahead and erase that. So that is what my sine graph would look like. So the 4 is changing, obviously, the horizontal distance. You can see that's or the compression. But now I can kind of like sketch a graph here of what the secant look like. I'm going to have my asymptotes again at 0, pi over 4, and now at pi halves. And then I'm going to have shared point here. Those are going to go down, approach the asymptotes. Okay, so we can look at the range and we can say, well, the graph never got changed vertically. Like just by reflecting it, that didn't change anything with my absolute maximums or my absolute minimums. So therefore, the range is going to be the same as the parent graph. -infinity to -1, union 1 to infinity. However, the asymptotes changed, right? Because instead of the asymptotes occurring at pi n, that graph got condensed. So what we're going to want to do is just go ahead and take what horizontal transformation, and all our horizontal transformations always occur inside the parentheses. So I'm going to set this to 4x is equal to pi n. And now I'm just going to solve for x, and I can see that x is equal to pi over 4n. And let's just make sure that that works, that makes sense. If n is 0, I have an asymptote at 0. If n is 1, I have an asymptote at pi over 4. If n is 2, I would have an asymptote at 2 pi over 4, which is pi halves. And you could see that it would repeat in the negative direction as well. So that works out. So all we got to do is set our interior transformations equal to our original asymptote equation. So our domain here is going to be all real numbers such that x cannot equal pi over 4n. All right, so the next one on cosecant is now going to have a phase shift, as you can see here. And again, we now have a horizontal compression down to 2/3 because that 2/3 is less than 1. So the period, though, is going to be unchanged. So I'll just write the period is 2 pi over 1, which is just going to equal 2 pi. I do not have a vertical translation. I'm not shifting the graph up or down, so I can just say my phase shift, though, is going to be pi over 4 to the right. All right. But now we need to, let's kind of conceptually understand what is happening here with this 2/3. So again, when we had that number was larger than 1, that vertically stretched the graph. Like in example number 1, instead of the graph going up 1, down 1, the graph now went up 2, down 2 because that stretch. Well, now it's compression. So now the graph is only going to go as high as 2/3 and as low as 2/3. And the nice thing about graphing these is you can make your scale however you want to. If the graph originally appears at pi over at 0, right, that's the initial period, starts at 0, well, then the new initial period now is going to be at pi over 4. So I can just kind of call the starting point pi over 4. And this endpoint now is going to be 2 pi plus pi over 4. And, I don't require my students to have these points or to clarify these points, but just to kind of show you for those of you that need to be able to graph this point is 9 pi over 4. Okay, but again, I'm just more concerned about understanding this shape. So that's really about it. You can see the start and the end of this initial period. If I wanted to find the x scale here, I would have to take my, I'd basically take my period, which is 2 pi, divide it by 2, which would be pi. So then I'd subtract that. So therefore, this angle is going to be 5 pi over 4. And then I could do that as well to find my x scale. Or you can see the x scale here is pi halves. So then you'd add pi halves to each one to get that x scale. But I'm not concerned about that. Besides that, all we have is that compression and then shifting to the right. So this graph is, again, just going to look something like this. So therefore, to sketch the cosecant graph, it's going to go up there. We have a vertical asymptote here. Vertical asymptote here. That graph now goes down. And then we have a vertical asymptote right here. So let's go ahead and knock out the range. So the range, the range of this function, you can see then again, it's going to go, it starts at negative infinity, and it's only going to go high as the minimum of the sine graph, which is at negative 2/3. So negative 2/3. And then that's union. It's going to start now at the maximum of the sine graph, which is positive 2/3, and it's going to continue all the way to infinity. Now again, we have a change in our asymptote, right? We have a horizontal transformation pi units to the right. So to identify my asymptotes, again, I'm going to just take whatever transformation I have inside the graph, pi over 4, and then I'm going to set that equal to pi n. Now to solve for x, we're just going to have to add pi over 4, right? Well, the problem is, can we add pi over 4 to plus pi n? And the problem is, no. It's like saying x plus 3 equals y. Like, you can't subtract the 3 from y. Like, that has a variable, and this doesn't. So therefore, they're not like terms. So therefore, our equation of our asymptote is just going to remain pi over 4 plus pi n. And let's look at that. You can see pi over 4 plus pi takes us to 5 pi over 4, plus pi is going to take us to 9 pi over 4. So you can see how that works out. And then the domain here is going to be all real numbers such that x cannot equal pi over 4 plus pi n. Okay? All right, so now we'll go ahead and look at some secant functions.